So I'm Davide Venturelli. I work for University Space Research Association, which is an institution I will introduce in a minute. And I have the privilege today to talk to you about what I think is the current state and the challenges and the opportunities for quantum computers to impact the domain of optimization. And just a disclaimer, since I also have an affiliation related to NASA, this is not a talk where I disclose the opinions of the government, nor the opinions of USRA neither. These are really my personal opinions. Feel free to reach out to me by email if you have comments, ideas, feedback, if you want to collaborate, if you want to discuss some topics. So let's get started. The outline of my presentation today is the following. I'm going to navigate a little bit the hype and the noise that there is out there related to quantum computing, starting with some background about me and my experience, and specifically I will discuss the problem of optimization. And I will discuss what are computers that could attack this in the quantum domain, introducing what's the general structure of a quantum algorithm, specifically heuristics, and what are the two main contenders for the near-term optimization approaches that could work in practice. And I will conclude with some info dump on resources and partnerships and government programs in the United States that should be in your radar. So about me and my institution, I want to say USRA is not as well known as NASA, but it has a long history, more than 50 years. Essentially, when the rocks from the moon landing came back on Earth, NASA realized that they did not have a vehicle to collaborate with universities, and they were all eager to study these incredible artifacts that came from the moon. So NASA and the National Academy of Sciences, they fostered the creation of this association of universities, which is now a non-profit corporation, which for over 50 years has worked with NASA and the Air Force and with the US government on space-related and aeronautics-related applications. And we are essentially bridging partnerships between NASA and academia and between private sector, and providing staff augmentation to NASA. So in this context, I work for the Research Institute for Advanced Computer Science, which is an independent institute of USRA, founded in 1983, where we focus on high-performance computing, artificial intelligence, and human systems integration. And that's where the quantum computing project, both at NASA and USRA, has kind of like started in the context of the NASA Ames Research Center, which created the Quantum Artificial Intelligence Laboratory, where I also work as a scientist. So after all this context, to introduce to you essentially the target of my research and my expertise, which is the problem of combinatorial optimization. So this is a definition you can find on the web. Combinatorial optimization is the process of searching for a minima or maxima of extremal points of an objective function whose domain is discrete but large. So the prototypical example of this is the traveling salesman problem, okay, which is very well known, but let me say a couple of things about it. You have cities across a map. Every city is connected by a potential road that has a certain length or cost associated to traveling that road. And what you want to do is you want to find the route that connects in a loop all the cities of your interest, minimizing the fuel cost or the distance or some metric across the individual roads. And of course, you can't try them all. You can't just, brute force the solution. That would require to try all the possible permutations of n objects, which is a factorial number, which is much larger than an exponential number as well. So you could see that you need to find a smart way and a smart algorithm to do that. And just for reference, I mean, these exponentially large problems, they have still received a lot of attention from the algorithmic community. And today, for example, the last time I checked, the traveling salesman problem has been solved for a specific very hard instance for 85,900 cities, but it took like a ridiculous amount of computation power. Now, these kind of problems are ubiquitous in industry, in real life as well. And examples of these kind of problems, they arise in telecommunication, in logistics, in finance, and in wireless networks, and so on. So this is the target for the computational problem that we want to solve. Of course, quantum computers can also be addressing other kind of problems, but this is the one where I focus on today. And what is the situation in terms of a very large picture situation of the field of quantum computing as of now? Well, if you are in this domain, or if you search a bit, you will hear a lot this acronym, NISQ. It stands for Noisy Intermediate Scale Quantum. It was actually introduced in San Jose, near Samsung, at a conference a couple of years ago by an eminent professor, John Preskill. It essentially states that we are in a situation where our current ability to manufacture these computers and to control their engineering and to understand their dynamics and mitigate the problems is such that we can create devices which have few hundreds of qubits maximum, some exception I will discuss, but that's more or less where we are, and whose fidelity of operation, which is the probability of error every time you try to do something in the chip, is 99% roughly, 99 point something. Sometimes less than 99%, depends what you're trying to do. So it's a situation where you do not have like large scale computers, and you don't have things that are really fitting your model with pen and paper in terms of computational power. So you want to go into what we call eventually the fault tolerant era, which is this holy grail of quantum computing, where you have a lot of qubits and you have a very low noise and very low probability of error. And in that case, you would be able to build a complex algorithm that fully exploit quantum mechanics. But we're not there yet. We'll discuss a few things related to that. However, when we will be there, we know for a fact that you will be able to achieve a computational power which is unprecedented in terms of complexity theory. There are some problems which are nominally so hard that it would be unthinkable out of the laws of computer science to solve them by a digital technology. And what I believe is that quantum computers will never be able to really solve these problems in their full generality, and that's the widespread belief among the scientists. However, I believe that, and it has been proven mathematically, that the space of problems that can be solved efficiently on a quantum computer is substantially larger than the space of possible problems that can be solved without a quantum computer. And we'll discuss why in a second, but this is a mathematical kind of a guidance of why we need to do quantum computing regardless. Okay, we have some indication that this is the best way to process information. So we need to go there. is similar to a space exploration. At some point, you need to go outside the Earth because you're, one very small thing in the universe. So there is also a kind of philosophically compelling reason to why doing quantum information processing, beside the practical applications. However, let me discuss with you the situation where you would have essentially a full tolerant quantum computer, and you would use its power to create an algorithm for optimization. Well, one of the cornerstones of what we understand about quantum computers today is the so-called Grover algorithm. Let me tell you a couple of things about this. So if you have an unstructured database, so you could think of it like as a scrambled phone book, where all the numbers and the entries of the people you're looking for are not in alphabetical order, and you're looking for a specific entry. Well, if you're in that case, then what you're looking at is the essentially a very dumb approach to search, because you don't have any guidance. All you can actually do is to do a search which is random. And if you're unlucky, you will find what you're looking for at the last try, which means that the algorithm, in terms of complexity theory, it's in this worst case scenario, linear in terms of the number of entries. Now, if you had a quantum database, and if you were able to do quantum queries, people have discovered in the in the end of it was 1996, I think, Grover specifically, that you would need only a square root of n trials, which is mind-blowing. Okay, I mean, that proves already that quantum mechanics is a tool which is more performant than any other tool you can think of in terms of digital computers, because there's no mathematical genius that can beat that in an oracle setting with a classical computer. And it's a quadratic speedup, and a quadratic speedup is nice. We know in industry that fast Fourier transform is used all the time with respect to its discrete counterpart because it has a quadratic speedup. And in general, these are the kind of things that enable the MP3 technology and other sort of things. So this is innovation that gives a quadratic speedup. So we are very excited about it. And we know that this could be potentially applied to most of the things you can think of in optimization. So that's very exciting. However, not too fast, because finally, because of the industry of quantum computing and because it's taken off for commercial applications, you do have essentially the opportunity here to look and crunch the numbers and see in practice how things are actually going to work. And this thing is essentially a very recent domain of research, which goes under the name of like domain estimation, or you could call it, resource estimations, or essentially practical implementations of quantum algorithms. And people are, for the first time, looking at really how many qubits you need, how much time it would take to solve a real world problem. And the results are scary, because we need billions of qubits, or if not, sometimes tens of billions of qubits, hundreds of millions of qubits. And we need, and this kind of like speed up would emerge only at such a scale, which is essentially beyond, many of the applications we might think of, certainly not high frequency trading, okay? So people are, the research right now is trying to bring this number down. And most of these numbers are due to the fact that you need error correction for executing this algorithm perfectly, which are extremely fragile with respect to noise and perturbations. And there's a huge overhead associated to the error correction. Now, I must say, error correction, despite being a thing that in reality is very futuristic because it requires technology we don't have now, I'm glad to report a couple of days ago, a breakthrough in that direction has been announced. So, things change all the time. If I have to give this talk, maybe, 1 year from now, I would be, these numbers might be cut by, I don't know, 5 orders of magnitudes. I mean, that's the nice thing about science. It always gets better, never gets worse. Okay, so now it might be kind of depressing to look at these numbers and say, okay, why the billions of dollars now if we need tens of millions of qubits, billions of qubits, and to have a quadratic speed up, and we're stuck at hundreds? Well, the reality is that there's a lot that you can do that you can't prove mathematically that it works. And in general, we see this in industry. If you have to solve a real world optimization problems, the chances are that you're not using the textbook algorithm that has been studied to death and people knows all the prefactors and the asymptotical results. Chances are that you're using some sort of black magic patchwork of things that work, but people don't know exactly why, and that has been partially commercial and proprietary, partially open source and something like that. And we also know, like, for example, the whole field of deep learning is essentially on shaky theoretical grounds in terms of the rigor of mathematical proofs, but still it works. And that's an entire industry that is based essentially on heuristics guidance. And so there's a huge hope in our domain to address the problem of quantum optimization with algorithms which are heuristics, whose computational power cannot be tested if not experimentally, empirically. So we need the quantum computers to know whether it was worth to create a quantum computer in the first place. It's a nice self-referential thing, but it's very motivating regardless. And I would like to guide you through a little tutorial of what is kind of a quantum algorithm, of this kind of modern quantum optimization algorithm that we're studying, and we're studying them with the NISQ device, the small scale devices, and we're learning in order to make them more powerful in the future devices that will be coming up in the next months and years. So the first thing we do in a quantum optimization algorithm is to create a superposition between all the solutions we're interested in trying to explore. So you have an exponential number of solutions. Remember the traveling salesman problem. And each solution is encoded in a bit string. 000 might be one specific route, okay? This is an example with 3 bits. So you have to imagine you have a lot of them. So you have an exponential number of them. But the rules of quantum mechanics allows you to create a state which has a mathematical property of being a vector, so an arrow, in a 2 to the power of n dimensional space. And every axis of this dimension, I can only visualize 3 here, but you have to think of 2 to the n of them, is a classical solution. Okay, so it's a solution with a well-defined bit string. So you're capable to create a state, which we call a superposition state, which mathematically is an arrow in this vector space. Okay, stick with me for a second if you don't know quantum mechanics. Now, to do this, it's not like esoteric. You don't need, incredible magic rituals. You can use technology which is now very well understood, and it dates back, I don't know, Nobel Prizes in the 60s. Okay, which is, for example, superconducting technology, which is one of the leader technologies of for the constructions of quantum computers. Specifically, just for the sake of completeness, if you take a metal which is known to become a superconductor at low temperature, what does it mean? It means that the electronic properties of the metal that typically govern its resistance, its specific heat, and so on, are such that at a lower than a threshold temperature, the electrons behave like a single mega electron, like they condensate in a kind of a almost incompressible fluid, and they move as a single quantum object. And then people have realized that if you take two superconductors and you create an insulating barriers between them, the exchange of informations between these quantum states of electrons is actually something you can control very well. And you can create an entire small circuit whose logical assignment to the electronics properties is allowing you to define some sort of quantum transistors. We call it qubit, right? And then you're essentially able to define a state of the circuit which is logical 0, a state of the circuit is logical 1, but also you can also create this arrow over the 0 and 1 axis, which are the classical states. And you can create this really in a scalable way using solid state technology and manufacturing techniques that are substantially present in a CMOS industry. So it's very exciting. Now, as I mentioned, so once you create this superposition state, you're not done, okay? I mean, because in reality, you're essentially doing something similar like random guessing, okay? So all the solutions you're trying to search are equally represented in your quantum state. What you need to do now is to influence and evolve and change the quantum state in such a way that it becomes closer in terms of vector representation to the state you're looking for. What is the state you're looking for? Well, it's the solution of your optimization problem. So it's the shortest road of the traveling salesman problem, for example. And so you need to use quantum effects and quantum operations to steer the movement of this arrow in this 2 to the power of dimensional space to come closer to a target state that you're trying to achieve. That's not easy, okay? But you can do that, again, by a well understood technology using superconducting qubits, for example, and using inductive couplings or capacitive couplings, or using, for example, transmissions lines and cavities that allow energy exchange. You can actually move the properties of a state which is having a description which is exponentially complex. It's 2 to the power of n. And then once you do that, once you once your state is substantially closer to the solution you're looking for, you can measure. And this measurement operation is something that essentially gives you a result with a probability which is dependent on how close the state that you moved is to the classical solution you're looking at. And it's something that makes a lot of physicists uncomfortable in terms of philosophical understanding. And our esteemed Richard Feynman, which is the myth of all physicists in some sense, is definitely quotable here when he said, like, if you think you understand quantum mechanics, then that means you don't understand quantum mechanics, because this measurement operation is clearly something that has to be more well defined in terms of the quantum theory. But in terms of a quantum computer, it is well defined as a readout circuit that at some point just shoots a signal to a qubit and extract an information, either 0 or 1. And whether it's 0 or 1 depends on the quantum state that you were able to create before. So you immediately understand, because of the probabilistic nature of the measurement in quantum mechanics, at the end of the day, you will run the quantum program many times, and you will get a solution with, you get an histogram, which represents a statistical distribution of possible solutions, okay? Of course, you're looking for one which is the best one, or close to the best one. And that might not be the more likely solution, okay? As long as it is, substantially more probable than just, going randomly, you are essentially winning to some extent. And this is an example of an histogram you could get with a probability distribution. And of course, maybe the best solutions are very, very tiny probability, but still, you're going to sample many times, and at some point, you're going to find it. And generically, the way we measure the performance of an algorithm like this, it's similar to what we do with classical black box parametric heuristics, which is essentially we're measuring the number of runs, of repetitions of the quantum algorithm that is required to reach a given solution quality, which could be defined by its approximation ratio or some sort of like metric of success with a given probability. So like, for example, people usually use the time to solution to 99% probability. So what's the expected time it's going to take for you to find the best solution possible with 99% probability? Okay, so this is an example of a metric people use to measure these things. Now, I want to say, I mean, this is a difficult business creating this quantum algorithms, okay? Because your algorithm needs to drive the state of a quantum system, which is described with an exponentially large number of variables. Indeed, you cannot simulate it. You can't really, design an algorithm by simulating it because it's exponentially intractable. And what you're looking for is one state, or maybe a polynomial set of states, like something very close to the optimal solution. And typically when you design a classical algorithm, it's not that difficult, like a Monte Carlo tree search or something like this, because the classical state description has a linear complexity most of the time. It's a bit string. Maybe you can do some flips. You can explore with a large neighborhood search. But in the end, you're always, at any given point, you're representing a single bit string, while a quantum computer has to deal with this huge number of parameters which are embedded in the description of the state you're manipulating, even if you don't know them, because you're not simulating this numerically, you're just implementing this physically. So the biggest question in kind of optimization, machine learning with quantum computers is, can the complexity of this state that we are manipulating through the laws of quantum physics shortcut the complexity of the problem you're trying to solve? It's essentially trying to, find a trajectory in this 2 to the power dimensional space, so almost infinite dimensional space, where you can avoid all the obstacles, all the local minima in terms of energy landscape, and just reach what you want. And you know that you can do this because the space is so large that there must be one direction where you can go. But good luck with finding it. But people are, have been moderately successful in finding some ideas on how to do that. Another little thing on how to measure quantum heuristics related to what I just said. So in general, you set up your algorithm with some parameters, and then you run it a number of times. You process the statistics of it, and then you look and say, the performance is not great. So you kind of change some parameters, and then you repeat until you're fine with the parameters you found. And then once you're fine, you're going to essentially run this for production. You're just going to try to achieve the best result. And once you have the best result, you need to compare it, if you want to do a benchmark study, against what you would have done if you didn't have a quantum computer. And, the first thing you could ask yourself is, okay, do I beat, does my performance is better than, I don't know, simulated annealing, or running, or I don't know, a greedy algorithm that I could have invented with a high school student? Okay, but not a totally stupid algorithm, not like a coin tossing. Okay, something that has some smartness in it. Well, if it doesn't beat that, I guess you don't even publish a paper. You might do a blog post or I don't know, a Stack Exchange post, okay? But you have more work to do. Now, if you are essentially beating at least one method that you could use if you were tasked to solve this problem, then you're in a situation where you can declare that you achieved a limited quantum speedup. So essentially you could say, oh, I have a speedup due to quantum computing, which is limited against a specific challenger. Okay, so it's not like, you know, against all possible algorithms, but, you know, against something that is well-defined. And typically you need to you know, optimize both things in order to compare properly. Not everybody does that, but still. Now, if you actually beat all the good methods you can think of, if you ask all your postdocs, all your collaborators, say, how would you solve that? Ah, use this, use this. If you try your thing against all of them, and you are substantially succeeding in beating the time to solution or whatever the metric you're using, then you can publish a press release and say, I have quantum advantage, meaning that whatever, you mean, if I'm tasked to solve this problem, my best way to do it that I can think of is with a quantum computer. Okay? There's still another question you can ask yourself. By how much I beat the rest? Because, I mean, a quantum computer is expensive, okay? And, you know, maybe you need a physicist to operate it. I mean, is it even worth it? Maybe you just buy more laptops or something like that. And if you beat by a crazy amount, meaning that all the computers on the planet together, or I mean, in general, if you beat by many orders of magnitudes, then you can claim what is called the quantum supremacy. You could say, end game, okay? You can't beat me, not even if you want, not even if you have $1 billion in doing this. So this is the nomenclature, the kind of jargon that people use to describe things. And I must say, as of today, I didn't check the last hour, but we are in a situation where we have few demonstrations of limited quantum speedup, and people are publishing, you know, advantages with respect to certain methods, with mostly quantum annealing. I'm going to say something, but there is also some exceptions on simulation, for example. And then there is no quantum advantage that, at least for my standard, has been really proven. Okay, you know, there's always a smarter way to do things that maybe has not been proven to be ruled out. Of course, it's a huge burden to prove a quantum advantage, because you need to prove that you're best with respect to all the classical heuristic you can think of, essentially. And then there is one demonstration of quantum supremacy by Google, which has been done on a problem which is made up to really demonstrate quantum supremacy, which is essentially the self-simulation of the computer itself. Okay, so it's kind of a very made-up problem, but it's very impressive from a technological standpoint, but it's certainly not for applications yet. Now, the quest, the holy grail everybody is trying to do in the applied quantum computing community is we want to try to find and discover and design and deploy and test and evaluate an interesting, useful application where we can see quantum advantage. Okay, so now that I explained a few things, you know, we can look again at this chart. We have a demonstration of quantum supremacy. Again, this is a demonstration which, yeah, it's an interesting story. The paper has been challenged multiple times by companies, Alibaba, by IBM. Initially, Google claimed that, you know, the separation in time required to match their performance would have been like tens of thousands of years. Now is down to days, but still, it's still impressive. I mean, like seconds to days, and people had like to invent fictional computers that don't exist yet to try to essentially demonstrate that it's not tens of thousands of years. And so substantially, quantum supremacy has been demonstrated, at least in one experiment. Quantum advantage, as I mentioned, has not been. There's a lot of emphasis right now in a metric called quantum volume. You might see press releases, which is a metric of capabilities, not a metric of performance, okay? So essentially, people are trying to say, well, my computer is capable to run algorithms which are requiring a certain number of qubits times a certain number of operations, which is a volumetric measure, okay? So people are measuring these things. Again, this is not related to performance, but it's one of the metrics which is simple to understand, a single number that that computers have you know, they use in their specs, window stickers. What's the situation according to me? Just this is again non-exhaustive list, personal opinions. Okay, so we do have three main domain of research in terms of applications. We have this futuristic fault-tolerant quantum computers. So some companies are targeting to build a computer that will be already, you know, in that regime. It's going to take 10 years or something, but they're committed to do that. There's a lot of research in this heuristics, and so a lot of companies are creating computers which are mostly targeting the performance also in proof of concept that we can do in this period of time. And then there's also companies that decided to exploit quantum effects, but to revive the concept of analog computing, which is way more easy to control, way more difficult to describe and understand in terms of performance, but way more easy to engineer. So, for example, we have also companies that have created quantum-inspired classical machines, okay, which are, you know, non-quantum, but they use principles that kind of mimic what's happening in some quantum effects. There are also other companies that are using lasers and interferometry, so classical coherent optics, but in a regime where some quantum correlations show up too, to try to prove that you can solve optimization problems like this. And I think it's very interesting. Again, these are all companies that can target already thousands of variables, if not tens of thousands of variables under control, because they do analog computing and quantum inspired, not really quantum, but still they might be onto something in terms of computational principles. Then there is all this superconducting qubits stack of companies that are trying to commercialize, actually they're commercializing quantum processors that either they work in the analog domain like D-Wave or IQM, a European company, or which is more in between digital and analog, or fully digital, fully gate model computer like Intel, Google, Rigetti, IBM. You have a field of technology development, which is called the cold atoms. So those are companies that decided to implement a qubit, not in a superconducting circuit, but to take natural qubits, like, you know, real world atoms, and isolate them, whether they are ions or neutral, and try to manipulate them with lasers or using their electrical magnetic dipole properties, and try to use them to do information processing. Very interesting approach. Of course, you don't have all the industry of consumer electronics, you know, you can leverage to the same extent as superconducting qubits, but very interesting approach as well. And then, as I mentioned, there are companies who are committed to kind of a longer term approach to quantum computing by developing computers that are intrinsically fault tolerant, and they have properties that, you know, require engineering breakthrough that we still didn't see, but hopefully in the next decade. Okay, I want to deep dive for a second on some algorithms that are used in practice. So one is the quantum annealing algorithm. As I mentioned, it's an analog algorithm. It starts with the formulation of an objective function for optimization problem, which is quadratic and binary. So essentially a polynomial form of this form, or a QIJ matrix multiplied the bit xi, bit xj. Now in physics, this is mappable to an Ising model. I'm not going to say more than that. If you're a physicist, you know what I mean. And you can add to this a transverse field, which is essentially a quantum signal on top of the classical energy landscape representation of the Ising model. In pictorial practice, what you have is a computer that starts with the superconducting qubits in a state which is a full superposition, which is all representing all possible solutions. And this is controlled by a quantum signal, a transverse field, which is progressively and slowly quenched. And at the same time, you have the energy couplings between these qubits, which represents the problem you want to solve, which is progressively raised to a level where at the end, the quantumness is zero and the energy of your problem is the maximum allowable by technology. This process, this analog smooth process of transition from a superposition state to a classical crystal state that represents the problem you want to solve, is called quantum annealing. It's derived from the idea of quantum adiabatic optimization, and is essentially an approach that is promising. Again, it's been implemented with superconducting qubits. It could be implemented also with other things, but this is the state of art right now. And of course, it's subject to noise, a lot of noise, as a matter of fact. So when you try to implement this, you have all sorts of misspecification in your circuitry, but still we see good results most of the time when we run these machines. One problem is in trying to solve a given computational challenge with these quantum annealing machines is that the structure of your problem you want to solve is not matching necessarily the structure and the layout of the chip, because since you're using the actual energy couplings between the qubits, which are implemented in the physical chip, what you need to do is you need to go through a mapping procedure where the computational and mathematical structure of your problem has to be embedded and substantially compiled in the chip structure, which is more sparse, which is more constrained. There's a lot of classical optimization things to do. So as a matter of fact, it might be larger the field of classical optimization for quantum computing than quantum computing for classical optimization, but still. This is an interesting game that we have to play every time we want to use this sort of machines. The D-Wave machine has also another interesting feature. As I mentioned, this noise that is essentially uncontrollable and always present might not necessarily be bad, because trying to solve a problem with quantum annealing is akin to do a cooling process of something that starts hot and needs to be cold. And when in its coldest state solves the problem you want. So a lot of research, specifically in my group, is also in trying to exploit the thermalization properties of a noisy open system. So you essentially, you can start the computation, then you can pause the computation for a few microseconds and allow the noise to essentially make you collapse in a thermal state, which is still quantum, but is thermal. And then, you move on. And we saw that this is essentially a good approach. Now, the good approach that people are starting is to hybridize quantum annealing with classical algorithms. So you start with a classical candidate solution, maybe something you found through a greedy linear algorithm, and then you initialize not in a superposition, but with that candidate solution. And then you introduce some quantumness, and then you take it off to measure again. And this reverse annealing approach has been proven in some applications in finance, in wireless networks, that has some advantages. Again, it's all empirical research. We're trying to detect the performance and test and evaluate in order to build upon it for future applications. And again, another breaking news. Today, there's also the annual conference of D-Wave, and they just announced a new chip. So they announced that now they are a 5,000 qubit chip, which seems like an incredible number compared to what I said before. But again, this is analog computing, so you have a lot of uncontrollable effects, so you can't really run all the algorithms you want. So that's why they can system engineer things which are beyond what, for example, Google, IBM, and others can do. But still, this is a very interesting development. So we can start to run problems which are quite interesting. This is really a snapshot of a few hours ago. They have a chip which can essentially prove, according to what they say, a speed up of about I would say 5 times with respect to the previous generation that we have at NASA. And it can solve problems which I would say are already in the hundreds of logical variables, logical bits, which is, you know, something interesting that starts to be in the domain of practical applications, borderline, interesting. Another thing I want to discuss very briefly, and then I will conclude my talk in a few minutes, is research in QAOA, which is quantum approximate optimization algorithm, which is essentially similar to quantum annealing, but where you look at the process where the quantum signal coexists with the classical signal, and you try to control it in a digital way. And you use gates and essentially a digital approach to do that, still subject to noise. Not precise as you would want, but of course, if you look at this literature, you need to understand what's a quantum circuit, which is a time representation of the execution of your elementary operations, which, as I mentioned, are gates. And again, the gates that you need to use in your algorithm are not necessarily the one that actually have been provided by the vendor that you chose to run your algorithm. There's a lot of compilation stuff that you need to do to actually decompose and represent the logical operations with the actual operations that are provided. You need to schedule the operations in time to try to squeeze the maximum power of the machine. All these things are very cutting edge, are very, you know, very low level in terms of abstraction, but very required to run problems right now on the machines. And if you look at these chips, they have some tens of qubits, and they are very different from each other. So if you build a compiler for one, it would never work for another one. So there's a lot of like research out there which is very focused on a specific chip, which has all its characteristics. Some qubits are working, some qubits are not, and some things can be done in one direction and not the other. I suggest you to look at these things. It's very fun. And this algorithm, QAOA, is currently running, I think the largest demonstration has been like about 30 qubits, roughly, almost 40. And it's still under benchmark. And that's by Google. This is a paper where you can see reviewed all the research has been done empirically on this. And I want to do a shout out to DARPA that launched a program to try to innovate and to try to push this method forward. It's called ONISQ. And I, as USRA, am leading one of the teams there with NASA Righetti on trying to achieve quantum advantage with the QAOA algorithm. And what we're using there is a variation of the QAOA algorithm that we call the quantum approximate, the quantum alternating operator ansatz, because QAOA stands for quantum approximate optimization algorithm. Everybody was calling it like the QAOA algorithm. So there's 2 A's. So we renamed it, and it's also more technically appropriate. And what we can do with our new version of it, we can actually look at problems which are hard constraints, not only problems which are unconstrained, like in the original paper. And this opens up scheduling, opens up SAT, all sorts of industrial opportunities. And there's connections between QAOA and QA, which has been investigated as of now by a lot of groups, because those algorithms are connected, despite one is analog and one is digital. Okay, so I'm at the end. I just want to, before opening the Q&A, want to say, please have a look at our NISQ Quantum Computing Newsletter. This is not a normal newsletter. This is just a digest of papers, which are categorized if you want to follow a specific domain. For example, machine learning. You want to know what's going on? Well, once a month, we publish this newsletter where we have about 50 papers in categories. And if you read those papers, you know everything that's going on. And I believe it's important to be, routed, to be oriented in the domain right now. And have a look at the government programs. As I mentioned already, DARPA ONISQ. There's another government program by IARPA, which is actually going under DARPA now on quantum annealing. There's a NSF large investment on these photonics architectures for optimization. You can find something on coheasing.org website. And one big announcement of last month is that the government has created 5 centers in the United States, funded for $25 million a year for 5 years to push forward quantum computing technology. I'm personally with NASA. Actually, NASA is leading the algorithmic part of the Superconducting Quantum Materials Systems Center at Fermilab. And this is actually a very interesting resource. So you can go on this website. You can see we're trying to build a new quantum computer with a technology which is quite unexplored yet, which uses 3D cavities to control radio frequency signals to interact with superconducting qubits. And that has its own advantages. It's very interesting. This is like 80 institutions which are collaborating to do that. So very exciting. I know how it sounds. Everything I told you seems, we need to do things like, compile things by hand. It does seem that the future of quantum computers is not super close. At the same time, this is something that we know it happened for example, massively parallel computation at NASA, exactly where I work most of my time. We had the computers that required all sort of overhead, all sort of tweakings done by hand to work in 1972. And people were even thinking, oh, it would never outperforms, wind tunnel. And instead, now wind tunnel is almost obsolete compared to fluid dynamics simulations. So there's a lot of co-design to be done between hardware and theory, and we're working on that. And with this, I conclude, and I open the floor for questions. These are my contacts. Feel free to reach out to me for any sort of partnerships we have.